Okay, welcome to the NUPOC video study guide number 106. All right, so today let's just talk a little bit about matrix math and some of the rules that we need to apply when we're, say, doing basic operations with matrices. So let's say, for example, over here I have a matrix that I'm calling matrix A, and it has 6 elements like this, arranged into 3 rows and 2 columns. So the first thing that we see is we have this little subscript, right? These 2 numbers on each element. So what we do is we always put the row dimension first and then the column dimension. So if you ever see a matrix with all these subscripts in it, or if you have to write out a matrix and keep track of the elements, right? This is the first row. So the first element in each subscript is 1, and this is the second row, so the first element is 2, and this is the second column here. So you can see that the second number is a 2 on each of these elements because they're all in the second column. So not only does that apply to all the elements within the matrix, but it also applies to how we describe matrix A overall. So since we have 3 rows and 2 columns, we would say that A is a 3 by 2 matrix. And then knowing these matrix dimensions allows us to basically make some predictions about if we're even going to be able to multiply this matrix by another matrix, or what the size of the resulting matrix is going to be, which might be useful. And just generally knowing the size of the matrix is useful for a lot of basic matrix operations. Okay, so here we have our matrix A, again, the same from the last slide there. And let's say we have a matrix B, which is 6 elements, but arranged in the opposite way. So B is a 2 by 3 matrix because we have 2 rows and 3 columns. So if we wanted to go ahead and multiply A times B, I would just write out my matrix A here, followed by my matrix B. But then how do we actually multiply these things? Because it's not just one number, it's 6 numbers here and 6 numbers here, and they're arranged in these columns and rows. So what we would do is take the first row, okay? We'd start by taking the first row of our first matrix and multiplying it by the first column in our second matrix. So what I mean by that is we would take A11 and A12 and rotate it 90 degrees so it turns itself basically into a column, and then put it right alongside this column here so it would look something like this, right? We've taken our first row from the first matrix, we rotate it, we put it alongside the first column in the second matrix. Then what we can do is basically multiply A11 times B11 and A12 times B21, add those 2 terms together, and that will give us if we're calling our resultant matrix C, the resultant of multiplying A times B, the element in the first row and the first column, right, of matrix C will be made up from this operation here, or will be the result of this operation here. So we can keep filling out our resultant matrix C by taking, if for example we want the second row first column, I would take the second row of A multiplied by the first column of B, and that would be C21. If I want the element of C, that's the third row and the third column, I'd take the third row of A multiplied by the third column of B, and that would give me C33, doing the same operation here. So we can already see that the dimensions of A and B are sort of convenient, right? When I take this first row and I multiply by this first column, I just have these 2 elements here, these 2 terms. So that kind of gives us some insight into some requirements of the matrix dimensions before we start doing a multiplication operation like this. So let's say I have A and B again here, and we've said that A is a 3 by 2 matrix and B, like we said, is a 2 by 3 matrix. Well, we need these 2, what we call the interior dimensions. So if I'm multiplying A times B, it's going to be a 3 by 2 times a 2 by 3. So this dimension, the last dimension in A and the first dimension in 2 are sort of going to face each other, basically. They're going to be back to back here. So we call those the interior dimensions of the operation. Those 2 need to match. So here we have a 2 in each place. So that works. We can multiply A times B. Now we have a 3 here and a 3 here. Those are what we call the exterior dimensions. And the resulting matrix, if we want to call it C in this case, will have these dimensions. So C will be a 3, as in 3 rows here, by 3, as in 3 columns here. It'll be a 3 by 3 matrix. Now, what if A was a matrix like this, where we had a 3 by 3 matrix already, right? So A times B would be a 3 by 3 times a 2 by 3, right? Well, the interior dimensions here don't match, so we can't do this operation. If we tried to do it in a computer, in a program or something, we'd probably get an error message saying something like the matrix dimensions don't agree. And that's because if, for example, I took this first row, say we were calculating the first element of our matrix C, all right, so I want to take the first row of A, multiply by the first column of B. Well, when I rotate this first row and line it up with this first column, I'm going to get A11 and B11, A12 and B21, and A13 and nothing. There's no other element of B to multiply it with. So this operation just can't take place. Okay. Now, if we had our two original matrices here, so A and B, let's say I wanted to multiply B times A in this case instead of A times B. So we're going to find that it's actually different. So A times B is sometimes not the same as B times A with matrices. So here, okay, we have B, so that's a 2 by 3 matrix, times A, which is a 3 by 2 matrix. Okay, so our interior dimensions, they match. We have a 3 here and a 3 here. So we can do this operation following the same steps that I was showing before, where we rotate the first row of the first matrix and line it up with the first column of the second matrix, multiply each term, and then add them together. So if this is all equal to some matrix C here, we can observe that C is actually going to be a 2 by 2 matrix because our exterior dimensions are 2 and 2. So even though A has 6 elements and B has 6 elements, right, our matrix C, the result of multiplying those two matrices together is actually going to be smaller than either of the two original matrices, right? So you could in fact have a large A matrix that is, say, one long row. It's just one big long row. And B is just one big long column, right? And they could have 100 elements in each one. As long as those two elements match, A might be a 1 by 100, and B, or whatever the second matrix here, would be a 100 by 1. They'll multiply together because the two interior dimensions of 100 would match. And since we have 1 here and 1 here, the result would just be a 1 by 1, or just one number. So it's kind of an interesting property of matrices. Now what if we went back to our original case where we had, instead of B times A, we had A times B? Well, we would end up with a 3 by 2 times a 2 by 3. Interior dimensions match again, but C now will be a 3 by 3 matrix, like you can see here. So C now has 9 elements in it instead of 4, like we had originally when we did B times A. So you can see that we can get really different sized resultant matrices depending on the order of operations, depending on the dimensions of the interior matrix, or of the original matrices. And it's just kind of good to have that kind of knowledge at your, basically easily accessible on the fly. So if someone gives you two matrices that are really large, but the interior dimensions don't match, you can just say, well, it's impossible. I'm not even going to attempt it because, you know, this one is 100 by 200 and this one's 150 by 300 or something. Or if someone asks you what are going to be the dimensions of the resultant matrix, you can quickly come up with that on the fly by knowing the dimensions of the original matrix. So I hope that's reasonably helpful, and of course don't forget to subscribe with this little button down here in the corner so you don't miss out on any of the upcoming videos. And I wish you luck in your next technical interview.